infinitesimally thin slice, which will be like a thin rectangle. And we're going to try and find the volume of that one slice that has thickness to it now, right? So let me draw a picture here of that slice. Here's my isosceles right triangle, but it has a little bit of thickness to it now, right? And I want to find the volume of that piece. What do you need to find the volume of this? Length times width. That's for a box. Okay, so you're finding the area. First, let's find the area of this triangle, right? Whatever that area is. And we'll multiply it times the width, right? If we do that, we're good? Okay, what is the area of that piece right there? Do you know anything about it? I mean, what do you know? Do you know any of the sides? Like how long they are?
Yes.
What do you know?
You know that two sides are equal.
Okay, I know this side is this equal to this side. I agree with that. What else do you know?
You know what the maximum is, that it can't be longer than 6 total.
Okay, so the most would be 6 and the smallest would be 0. Yeah. Okay, yes, I do agree. But let's move this thing around. It can be anywhere. Do you know the distance between here and here? If I move that around, what is bounding me on top? Some curve, right? What's bounding me on the bottom? Some other curve. Can you come up with the equation of the curve on top? How?
Divide the other two?
Solve this for...
Half of it. The top half.
Solve for x and for y.
Okay, if I asked you to graph y equals square root of x, you know what that looks like, right? That would be a curve up here. If I do x squared, you know what that looks like, right? Y equals some function of x. We know how to graph things like that. An ellipse is not a function, but we could still solve for y. Try and solve for y here. You're going to wind up with a plus or minus, aren't you?
Yes.
That's okay. Bless you. Bless you. All right, that's enough. You get 2, not 3. All right, that's solving for y. We get plus or minus, right? Everyone follow what I did? Okay, the positive one of those draws the upper half. The negative draws the lower half. So if I look at these as two completely different functions, one will draw the top, the other one draws the bottom. Does that make sense that that would work that way? Yes? So this is actually, I could look at this as being a function. I'll call it f of x equals the positive root of 9 minus 9/4 x squared. And the bottom one I will call g of x is the negative root of 9 minus 9/4 x squared. Do y'all buy that? So now we're back to, I mean, what if I was asking you to find the area? You would just do integral, you do top one minus bottom one, wouldn't you? The top one minus bottom one is the distance here. So you know this hypotenuse, don't you? This hypotenuse is the same as this distance from here to here, which will always be what? This minus this, which is basically doubling that, isn't it? Right? If I take this and I subtract a negative, I'm going to get plus. So it's 2 of them, not squared, doubling. Yeah. So would you agree that this distance is 2 root 9 minus 9/4 x squared? Yeah? I'm still trying to find the area of that. So when it comes to an isosceles right triangle like this, it does follow that these two sides are the same. We usually say a squared plus b squared is c squared, But could I say A and A because they're the same? And could I say C over here like that? Yes. And so A squared must equal A squared plus B squared. Oops, 2A squared. A squared plus A squared must equal C squared. Do you know any of these on that triangle?
Yes, C squared.
You know the hypotenuse, don't you? The hypotenuse, this is C, isn't it? What I'm trying to do is find out what one of these sides are. Because you told me, I think some of you said, that the area of that triangle is 1/2 base times height. So if I find one of these sides, I'm done, right? One of those sides? So I'm going to solve for A, but I know that C is this. So 2A squared equals this squared. 4, and then what happens when I square the root? Goes away. 9 minus 9/4 x squared. Divide by 2. What do you get when you divide by 2?
4, not giving me 2.
You get A squared is 2. 2 times 9 minus 9 or x squared. And then square root it. And guess we're going to be back almost to where we just were. A is going to be root 2 times root 9 minus 9/4 x squared. That's what this side is, right? That's what that side is, but that's what that side is also. Okay, so what is the area in red here? What is the area of that triangle? You told me that the area of a right triangle here, this area would be 1/2 base times height. But the base and the height are the same, aren't they? So this is the same as 1/2 AA, which is 1/2 A squared, isn't it? And don't we already know A squared? It's right here. I didn't actually need A. I was just showing you that's how we could solve for A. So it's half of this. Take half of that and the 2 goes away, doesn't it?
Isn't the base the hypotenuse though?
No.
No.
No, because look, if I draw a right triangle like this is the base, this is the height. The hypotenuse is not the height.
Aren't we looking at it from the hypotenuse? Like we're looking at it like, oh, okay, so the hypotenuse ends up being the base. We have to find the height that way, right?
No. Well, yes, we could, but that would be more work. We could look at this as being the base and then go try and find that height, but I don't need that because if I turn it sideways, here's base, here's height. You get the same answer either way.
No, I was just saying because, since we're looking at it from the hypotenuse,
Mm-hmm.
and it's like exactly like that, that's where...
The only thing that this being the hypotenuse did for us is it allowed us to figure out what the length of that side was in terms of x. Other than that, the way you get the area of that is up to you. I just felt that was easier to do it that way. Okay, so the area will be what? 9 minus 9/4 x squared. It's half of this. That's the area of one little face here. And to get volume, I multiply it by the width. How wide is this little infinitesimal strip? dx. Right? dx. So the volume of this is going to be 9 minus 9/4 x squared times dx. Right? I'm out of room. That's the volume of that one little infinitesimal sliver slice thing. And I want to add them all up. So I've got to move my slice all the way from the left to the right. So it's going to be an integral because I'm adding things up. It's going to be with respect to x, so I'm doing all those volumes. Here are all those volumes right there. That's the volume of one of them, right? It's this. And I'm going to let my x vary between -2 and 2. And that's it. Now you picked that one. That was a little harder than I would have done. What you need to be able to do is, my region will be a little bit nicer than this, okay? It'll be nicer. What you need to be able to do, though, I'll give you a quick example in a picture. I'm trying to give you an easy one without giving it away. Let me see what I put on the test. How about we do this?
What?
Let's do this one.
What number was it?
Look at this region bounded by y equals x, y equals 1 minus x, and x equals 0. That's the base of the solid. So let's draw that real quick. Y equals x is the diagonal. And then 1 minus x is that, right? And then x equals 0 is
Just the y-axis.
the y-axis. So you're talking about this region in here, right? That region right there. That's the base of a solid. Here's what I'm going to tell you. Cross sections form squares. Give me the volume. All right? So this is y equals 1 minus x. This one is y equals x, right? I take a cross section, I cut through like this, and it forms squares. So think about what that square would look like. My slice comes through here. I'm looking for a better color. Here we go. If I slice through like this, okay, little rectangle, and imagine laying that down on the ground, okay, and then looking, and it forms a square. Then it would go, what? Up, back, and down. It would form a square, right? All sides the same? I should put here squares. Do you know the volume of this little infinitesimally thin little slab there? Okay, you know the width is dx. That's always going to be dx. But then you need to find the area of that face.
Length squared times dx.
It's just the length, right? It's the length from here to here times itself, because it's a square. Do you know this length?
Yes, it is.
It's this, right? It's this top minus bottom. So what's the top function? 1 minus x minus what's the bottom function? X. So what is 1 minus x minus x? 1 minus 2x. Do you agree that that's how long this is? 1 minus 2x? I'm taking this and I'm laying it down on the ground and making a square. And then I know that this length is the top one minus the bottom. So if this is 1 minus 2x that side, then this side, since it's a square, must also be 1 minus 2x. So the volume of that would be, the volume of that little slab would be 1 minus 2x squared dx. Got it? To get the total volume of the entire solid, integral where to where? What's x starting at here? 0. Where does it stop? Well, where they hit each other, which is 1. 1? We think 1? No. I think it's a half. 0 to a half. That you would have to find that point of intersection, wouldn't you?
Yes.
Okay. You could set the two equal to each other. And then 1 minus 2x squared dx. That would be the answer. Do you all understand that? No questions? You sure? Okay. Well, that's the first thing. Now, let me do the same exact region. Let me change this to something else. What if I did semicircles? If I did semicircles, the only thing that would change is this formula, because the thing laying on the ground is no longer a square, it is semicircle. It's a half circle like this. And then it's got some thickness to it like that, right? So that's the only difference. It still has the same width of dx, but you need to find the area of that little half circle. So what is the area of a circle? Pi r squared? But then we want half of that. So we want half of pi r squared would give me that. So I need to actually know that radius, don't I?
Yes.
The radius, not the diameter. Do you know the radius of that circle? What is it? It's half of this distance, isn't it? And that distance was 1 minus 2x. So it's half of that. So the area of that will be 1/2 pi times the radius you said was half this distance, 1 minus 2x, half of it, squared. Do you see the contrast, the difference between these two formulas here? Now, if I'm looking for volume, I'm just going to throw the dx on the backside of that to give me my volume. That right there, though, is half the area of a circle. 1/2 pi r is half of the total distance from here to here, which we knew was 1 minus 2x. That's this, squared. And you could do some cleaning up here, like you could square the top and bottom, do all that. But at the end of the day, you're going to be just setting up an integral. It'll still go from 0 to half, won't it?
Yeah.
And I can pull some constants out. Pi is a constant, that can come out. I actually want to pull the 1/2 out, but I'm going to square the top and bottom here. When I square the bottom, what do I get? 4. Can I pull that out with a 2 on the bottom? Make that a 1/8? I'm going to make that a 1/8. And then the only thing left in here is that top piece squared, right? I'm just going to write it like that. 1 minus 2x squared dx. That would be the formula if you were doing semicircles. What if they were full circles? Just double that, right? So then it would be like this. It would be, here's the base, but instead of doing a semi, and this would be weird because it wouldn't be the base anymore. It'd go like that. But you get the idea. If it was full circles, then the only change in the formula would be you would not do 1/2 out here, right? What if they were? What if these slices were equilateral triangles? This is the last one I'm going to show you. Equilateral. That's triangles. Okay, so I know the base still, right? I still know that this is my base. Equilateral means all sides equal length. And it has a little bit of thickness to it like that, right? All sides equal length. And we know the side is what? 1 minus 2x? You need to find the area, though. Don't you? You need to find the area of this little face. So you need the area of an equilateral triangle. There's 2 ways to do it. One's hard, one's easy. So let me remind you here, if you have an equilateral triangle like this, you could make 2 right triangles out of this and double the answer. Or the easier way is to use a formula from pre-cal that allows us to do it much quicker. Do you want to see both ways or just short way? Just the short way? Okay, there's a formula. It's on your formula sheets. There's 2 formulas. If you have a triangle, if you know the base and you know the height, then area is base times height. But we don't know the height here, do we? We know the base. We don't know this altitude, the distance from here to here, do we? So that formula is great. If we know that, we don't. So instead, I'm going to use this other formula that says that the area is 1/2 AB sine theta, where the angle is in radians. Well, it doesn't matter if it's in radians or degrees, actually. So what's great about this formula is that if you know 2 sides and the angle between them, then you can find the area of a triangle. You just need two sides. So do we know two sides of this triangle? Yes, because they're all the same sides. 1 minus 2x, 1 minus 2x. I only need two of them. And I need to know the angle between them. 60, because it's equilateral, all angles are going to be the same. 180 degrees, divide that by 3. So you get 60 degrees. So now I come back over here. The area of this is 1/2, and then 1 minus 2x, that's a, times itself again, so squared, sine of 60 degrees, which is root 3 over 2. Sine of 60 degrees is root 3 over 2 from pre-cal, which is equal to, if I move this out front, root 3 over 4 times 1 minus 2x quantity squared. That's it. That's the area. And then you have to multiply by the thickness to get volume, right? And then you integrate. So our answer would be integral 0 to half, root 3 over 4, 1 minus 2x squared dx. That's more like what you'll see on the test. I'm not going to ask you for all these different shapes, but your region's going to be a lot easier to work with, okay? And then you just need to know how to deal with, I don't think I'll go outside of what I've shown you. Squares, semicircle, circle, equilateral triangle, isosceles triangle, nothing else really, all right?
Once we set up your integral,
That's it. You don't have to evaluate it.
We could have easily split it down to equilateral triangle, right? And the base half, you already know the hypotenuse, and then just a squared plus b squared, right?
So you're saying we could have gone the longer way, which would be to cut that in half.
Right, you already know that the base is half.
So this would be,
1 minus 2x over 2, you already know the hypotenuse. It's
the hypotenuse is 1 minus 2x, because all sides are the same.
Pythagoras theorem.
And this is the height which you're trying to find. So you have to do 1 minus 2x squared plus h squared must equal 1 minus 2x squared.
If we didn't know the formula.
Yes, I'm going to go all the way. 1 minus 2x squared over 4. I'm doing that. Plus h squared equals 1 minus 2x squared. I'm going to move this to this side. Okay, and notice that it's this and this are the same, right? Did y'all see that? This over 4, this over 1. Numerators are the same. So I can get a common denominator between those. And when I do that, I would get h squared equals 4 times 1 minus 2x squared over 4 minus, I brought this one over, one of those 1 minus 2x squareds over 4. And how many of those do I have then? 3 of these 1 minus 2x squareds over 4. And then I take the square root and I get root 3 over 2 times 1 minus 2x squared, but I take the square root. And then that's h, right?
If we didn't know the
Yes, but I want to show you, this is good. That's h, but this is the base. So multiply this times this, and what would you get? Root 3 over 4 times 1 minus 2x squared. Is that what we had? It is? Something doesn't seem right.
Don't we need to multiply the base?
Don't we need to double this?
Yeah, because we halved it in the beginning of the base.
1 square root. Okay. I don't think you want me to invest more time. They should match up. I don't see, there's something seems off on that. Because ours was what?
Same thing.
Yeah, but that was only half the triangle. That's the thing. Remember we had taken this and we had cut it down the middle and we had looked at just this part. So we should have doubled that, which would have been root 3 over 2. Didn't we have root 3 over 4? Oh, did we never do 1/2? Oh, we never did 1/2 base times height.
Right.
Yes, okay, so it matches. Good. Let's move on. What else do you want to know about? Yes?
The improper integral that was bounded.
Improper integral? How about this? Something like integral 5 to 8 of 1 over x minus 8 to the 5th dx. The dangerous thing about this is that a lot of people don't recognize that this is an improper integral. They don't realize that if you plug 8 in, it's undefined. So we have something really bad happening at one of the endpoints of the interval of integration here. So how do we deal with that? Look at a number line. Here's 5, here's 8. Where's the problem happening? At 8, so that means we're going to need to approach 8 from the left side, aren't we? So the way I did this in class is I set up a limit. I let t approach 8 from the left, right? T approach 8 from the left of this integral with the 8 replaced with t, 1 over x minus 8 to the 5th dx. And now you have to find the antiderivative. What is the antiderivative of 1 over x minus 8 to the 5th power?
5 over x to the 8, or x minus 8 to the 4th.
You say it again? I think you're on the right track.
You bring it up. A negative 5.
Okay, so let's bring the limit still. This really right here looks like integral of 1 over u to the 5th. Right? That's really what it kind of looks like. And this is really integral of u to the negative 5. So antiderivative of that would be negative 1/4 u to the negative 4. Right? You have to add 1 to that. And then, okay, so this should be negative 1/4 u, which is x minus 8 to the negative 4. And then I'm evaluating that at 5 and at t. And then I'm going to let t go to 8 from the left at some point. Questions? All right, let's plug in and see what happens. I'm still going to have a limit here. Limit t is going to approach 8 from the left side. And then plugging t in, I get negative 1/4 t minus 8 to the negative 4. And then minus what I get when I plug in 5. So negative 1/4. 5 minus 8, is that negative 3?
Yes.
Okay, hold on. I'm going to say 5 minus 8 to the negative 4. That. Is that okay? How about this one? Let's do this one first. This is really negative 3 to the negative 4, right? Negative 3 to the negative 4. That's the same as negative 1 over negative 3 to the 4th, which is 1 over 81. And then times negative 1/4, and then times negative. So this will really be plus 1 over 4 times 1 over 81. Do y'all agree? That's this part.
Negative 81, it's negative 3 times negative 3 is 9 times negative 3 is negative 8.
But there's 4 of them, so it should be, yeah.
Sorry.
Oh, that's all right. And then whatever that is, who cares, right? And then this, see, this is where we're going to have a problem, though. If we plug in 8, right into here, you get 0, right? So you, oh, 0. 0 to any power is 0. Who cares? That's not right, because this is really 1 over. So this is really negative 1/4 times 1 over t minus 8 to the 4th, right? And when I try and plug in 8 here, I get 0, and that gets infinitesimally small down here. And 1 over 0 is going to do what? It's going to explode, right? As we get closer to 0, it's not actually 0 because it's a limit. That's going to get really big, which means it's going to become infinite, right? And so this is going to go basically to infinity. Negative in front is going to make it negative infinity. Who cares? The whole idea is that it diverges. It does not converge. So the answer to this is that it diverges. Now you will also need to be able to handle one of these when it converges. And there are examples of that in the book on page 360. I believe number 25, no, number 24, and I believe number 25 also are examples of convergent improper integrals of this form. All right, we're just about out of time. Anything else?
So there's different formulas for disks, shells, and then for the arc length and surface area, so we have to know those like 4.
Yeah, there's about, what, 5 formulas, I think, total that you really have to know, right? What are they? I mean, in general, you have, if you're trying to find, F and G, right? If you're trying to find the area, it's integral a to b f minus g, right? That's basically the idea. You subtract the 2. What if you were going to take this and you were going to rotate it about the x-axis? The volume would be, well, what method is that? You go in washers, so you would go pi integral a to b. It would be your outer edge minus your inner edge, right? Squared each one, and then whatever, dx. So that's kind of another formula. What if you were rotating it around the y-axis? So you go shells on this one, which shells would look like 2 pi, a to b again, out minus in, which is really like top minus bottom, but then this important piece right here is your radius, which is the distance from the axis of rotation to the rectangle, which in this case would just be x. But if I move that line, it could really change. It could be a lot of different things, yeah. What else? I only have 3 formulas. Oh, arc length, okay. So the arc length is basically your integral a to b square root 1 plus derivative of function squared dx, and then the surface area would be same exact thing as this, except 2 pi in front, a to b, f of x, right, in front of that square root thing. These are so similar.